to present now applications of the kinematical conservation laws. Now all the work which I describe here, they were developed at the Indian Institute of Science, Bangalore. The kinematical conservation laws forms an undetermined system of equations, underdetermined system of equations, and to use the kinematical conservation laws we need a determined system, additional equations which can be derived only from the dynamics of the curve omega t, which comes from the equations of the physical system in which it propagates. We first present the closure relations of the kinematical conservation laws for some physical system using a small amplitude high frequency approximation. We shall denote the non-dimensional normal velocity of a wave front by a small f and a small m, and that for a shock front by a capital M. Geometrical optics consist of construction through high frequency approximation, which was first applied in 1911 by Sommerfeld and Runge to the wave equation, and that is seen in Courant and Hilbert. The high frequency approximation, when applied to hyperbolic partial differential equations, gives a representation of the solution in terms of a wave amplitude w and phase function phi. The phase function satisfies the Eikonal equation, with the help of which we can define rays, and the state variable u can be expressed in terms of an amplitude w and the unit normal n of the wave front, phi equal to phi x t equal to constant. When the expression for u, that is the dependent variable, in terms of w is substituted in the hyperbolic system, we get a transport equation for the amplitude w along the rays. These are the ray equations dx dt equal to n a 0 and dn dt equal to 0 for the wave equation. And the transport equation which I described on the last slide, the procedure in the point 3 gives dw dt equal to a naught curvature of the front multiplied by w, and that is equal to 1 divided by 2a dA dt into w, where omega is the mean curvature of the wave front and a is the ray tube area of the rays. The omega, the curvature, is given by minus 1 by 2 divergence of n. Equation 2 gives an expression w equal to w 0 divided by a to the power half, where w 0 is constant and the small amplitude assumption breaks down when the rays tend to meet, in which case at the caustic when a tends to 0 and w becomes infinite and the small amplitude assumption breaks down. The same result, that is the small amplitude assumption, breaks down in classical expansion described above, is also seen in the case of quasi-linear hyperbolic equations. Then we do not get the experimental results which were obtained many years back by Sturtevant and Kulkarni, where the amplitude actually remains finite, and this is the experimental result which is not obtained by this high frequency small amplitude approximation. Hence, with the next slide, weakly nonlinear ray theory, and this is the work started from 1975 and is explained well in detail in the reference 7. The basis of the weakly nonlinear theory applied to the hyperbolic system, which I write here, this equation number 4, for a wave in a mode having genuine nonlinearity is to capture the wave amplitude in the Eikonal equation itself. Now, there has been systematic derivation of weakly nonlinear ray theory by the procedure which is very long and very involved, and it is available in reference 5, but it is there is simple algorithm also in a paper which is in reference 3. The weakly nonlinear ray theory is in contrast to the work of nonlinear small amplitude perturbation of Vidham, Shakebruwa, Parker, Hunter and Keller. Unlike the above work, the rays of the weakly nonlinear ray theory satisfies Fermat's principle that the time of transit should be stationary along a ray with respect to the neighboring path. We write the weakly nonlinear ray theory equations for the Euler equations of the gas dynamics. Okay. Let me not describe the details here, but write the final equations here. Eigenel equation of the linear perturbation gives phi t plus a naught modulus of phi equal to 0, and amplitude does not appear here. The original Eigenel equation characteristic equation is given by phi t and inner product of q gradient of phi a modulus of gradient of phi equal to 0. And when we substitute the small amplitude approximation here, in this Eigenel equation we get another new approximate Eigenel equation which is phi t plus a epsilon gamma plus 1 divided by 2 omega tilde modulus gradient of phi equal to 0, and omega tilde is the small amplitude perturbation which has dimension of velocity and is of order of 1, by small amplitude comes from epsilon here. Note that we have captured the wave amplitude W in the Eigenel equation. This is the Eigenel equation and we have captured the wave amplitude. Now, the ray equations derived from this Eigenel equations are given by dx dt plus what was there in the linear theory plus one additional term, and then rate of change of normal is a completely new term appears here, which contains the tangential derivative of W tilde, that is the amplitude, and the transport equation comes out to be dw tilde dt equal to this ddt is a big expression here, but that does not matter here, just see dwt dt equal to curvature multiplied by a naught multiplied by w tilde, where the L operator is of course the tangential derivative, where in the transport equation 10 omega is now the mean curvature of the nonlinear wavefront omega t. The components of the operator L represent tangential derivatives on the surface omega t. The presence of the term minus epsilon gamma plus 1 divided by 2 L operating of omega 2 in equation second part of the equation 9 makes the rays of the weakly nonlinear ray theory to satisfy Fermat's principle, and that is the important part of this theory. We shall now consider 2D kinematical conservation laws and 3D kinematical conservation laws based problems separately. These are the problems which are solved by 2D and 3D KCL based theory. These are weakly nonlinear ray theory and weak shock ray theory. I go to two-dimensional kinematical conservation laws and its applications. The two-dimensional kinematical conservation laws are g sin theta t plus m cos theta xi equal to 0, g cos theta t minus m sin theta equal to 0, where m is properly defined non-dimensional front velocity. The closure relation 10, which is earlier written here 10 for in the differential form for one case is written earlier. All closure relations come basically from the energy transport equations, and in order that they are useful for KCL theory, we must write their physically realistic conservation forms. Now, I write the physically realistic conservation form of the three problems, three applications. One is weakly nonlinear ray theory for a nonlinear wave front, and it is given in this form m minus 1 whole square e to the power 2 m minus 1 multiplied by g, and the whole thing differentiated with respect to t equal to 0. That is one conservation. Next is motion of a crest line of a curved solitary wave on the surface of a shallow water, and this is given in the form m minus 1 3 by 2 e to the power 3 by 2 m minus 1 g, and whole thing differentiated with respect to t equal to 0. Then there is a shock ray theory of a curved weak shock front, and this consists of two equations. One is written number 16 here, it is a long equation. Another equation written here 17, which is another long equation. M equal to m here for a shock front, and mu which appears here and here is a measure of the gradient of the flow variables behind the shock. Now, I discuss the nature of the 2D weakly nonlinear ray theory equations and 2D SRT equations. 2D weakly nonlinear theory and 2D SRT equations form a hyperbolic system with when m is greater than 1 or when capital M is greater than 1 respectively. This is because 2D weakly nonlinear system of 3 equations has 3 distinct eigenvalues. 2D SRT system of 4 equations have 2 distinct eigenvalues and 1 double eigenvalue. The double eigenvalue has 2 linearly independent eigenvectors. In both cases, the nonlinear wave front and similarly the shock front move in a medium ahead of it when the gas pressure is less than that behind the shock front, behind the front. Now, let me describe an algorithm to use the KCL to find the nonlinear wave front. The nonlinear wave front is given here, and you take any point x naught y naught here. On the nonlinear wave front, the distribution of m 0 at t equal to 0 on this front is prescribed. The geometry is prescribed, therefore, theta 0 is prescribed, and also all these are prescribed as a function of t, and we choose a coordinate xi on this front. Now, then we start from a point x naught y naught and move along a ray by using the first part of the ray equations and reach this point. When we reach at this point at time t, then we use another set of equations, another part of the ray equations, and move on this generate. When we have reached this point, then we integrate the another set of equations and generate the curve omega t at this point, at this time. Okay. That is all described here. Okay. Now, a summary of 2D results. One is remark, this comes the conservation formulation of the ray theory, that is 2D KCL, gives rise to hyperbolic system of balance laws for m greater than 1, Analytical and numerical investigations reveal many fascinating geometrical features of the fronts available in the two books 7 and 11. Very successful in modeling several physical problems. Propagation of a weakly nonlinear wave front in a polytropic gas, propagation of a curved weak shock front, a motion of a crest line of a curved solitary wave in a shallow water. We have a new formulation of the sonic boom produced by a maneuvering aerofoil as a one parameter family of Cauchy problems, and this is a very sophisticated and very nice formulation of the sonic boom in mathematical language. Resolution of a caustic. Firstly, I would like to, before coming to this slide, I come to the previous slide. If you have a moving curve or if you have a wave front which is a straight line up to this and then a straight line up to, after that meeting at a point this at the point here, then after some time if you use the linear theory, it folds as seen here, it folds like this. But when you use the weakly nonlinear theory, the same wave front now has no fold. It this is the at t equal to 0 and this is at t equal to greater than 0, and then it has a no fold, but two kinks appears and the rays move and then change the direction, become parallel to the x axis at the kink, and then the amplitude, since there is no convergence of the rays at a point, the amplitude remains finite, and this is a very special feature of the weakly nonlinear ray theory. In the sonic boom problem, we have airfoil or aircraft moving on a curved path, and this at this point it takes a different direction. The upper part of the aerofoil, the aerofoil is shown very small here. The upper part of the aerofoil gives a sonic boom which goes up like this, and after it has turned the direction, the sonic boom you can see here. The lower part, the sonic boom from the lower part of the aerofoil nose, you get the sonic boom which is of this type. Okay. But what you find, if it was a linear theory, a folding of the wave front would have happened, but in the nonlinear theory there is no folding, but two kinks appear, which you can see here, two kinks appearing here, and there is a folding here in the linear theory. But this is physically realistic, this is not correct, and such a fine picture you cannot get by any theory other than KCL. KCL reduces the 3-dimensional problem in xy space to 2-dimensional, which leads to great saving in computational time and also robustness in the numerical scheme. First, we considered weakly nonlinear ray theory in a polytropic gas. The basic equations are here, but the conservation form of the energy transport equation is written in this form. And this conservation law now closes the KCL. Therefore, we have the KCL here and the energy transport equation here, and then of course, we have the constant, which is not very important, because once it is satisfied at t equal to 0, it is satisfied for all the time. Therefore, we have the KCL system here. Okay. Now, the eigenstructure of this system, eigenstructure of this system is described in this theorem. The eigenvalues can be obtained by differential form of the conservation laws. The eigenvalues are given by lambda 1, lambda 2, but lambda 2 equal to minus lambda 1 and lambda 3 equal to lambda 4 equal to lambda 5 equal to lambda 6 equal to lambda 7 equal to 0, where lambda 1 is given by this expression. It's a complicated equation, but it was quite difficult to get it, but now the expressions are given here. We summarize the results of the eigen space as follows. Next theorem, 3D weakly nonlinear ray theory system has 7 eigenvalues, which I have described: lambda 1, lambda 2 equal to minus lambda 1, and then lambda 3, lambda 4 etc. up to lambda 7 equal to 0, where lambda 1, lambda 2 are real for m greater than 1 and purely imaginary for m less than 1. The 4-dimensional, further the dimension of the eigenspace corresponding to the multiple eigenvalue 0 is 4. These equations are now hyperbolic but degenerate hyperbolic for m greater than 1. This is an important theorem, completely describes the nature of the equations of weakly nonlinear ray theory. It shows the system is degenerate. It would require considerable effort to solve it numerically, even when in the case when m is greater than 1. We need to develop a numerical method which respects the geometrical solenoidal constant also. That has been done. Now, we go to the 3D SRT in a polytropic gas. We skip this part, but simply state that we get a system of 8 conservation laws which has 8 eigenvalues with 7-dimensional eigenspace. Now, we show the accuracy, robustness of our method and 2 results. Now, this shows the accuracy. This is the solenoidal condition should be 0 all the time if it is initially chosen to be 0. Our numerical approximation preserves the geometrical solenoidal condition almost to machine accuracy, This is true for all numerical results which you get, and the machine accuracy you can see is the results of one component is 10 to the power minus 15. That is very good. The divergence given at t equal to 10, the error is up to the order of 10 to the power minus 15. Now, I show 2 beautiful applications of the KCL based propagation of curves, which are here shock fronts in 2 and 3 dimension. In 2 dimension, we have a sinusoidal initial wave front or shock front, and then these are smooth, and then the rays start from different points of it. The first from this part they diverge, then from this part they converge, and when they converge they form a pair of kinks which you can see here. One upper kinks move up and the lower kink from this part move down, and they interact at this point according to solution of the Riemann problem of the KCL, and that is the exact solution Riemann problem. And then when they interact, this break into 2 separate kinks, or they separate out 2 kinks and they move further. This process of interaction and separation and formation of the pair of kinks and moving away from each other is repeated again and again, and finally the front becomes almost plane. Now, that I go now to the corrugational stability by shock ray theory, KCL based shock ray theory. What I show here, it is almost impossible to get the following results by any other method. its real power of method for tracking evolution of a surface. We see we have a smooth sinusoidal surface extending to infinity in all directions, but it has in each period it has this shape. Initially it is smooth, but at t equal to 10 the kinks appear and the surface takes a form of like this, and these are kink lines. Actually these are two kink lines here, two kink lines here, two kink lines here. The kink lines first interact and then start moving apart and the surface takes this shape. Again the kink line come and is about to interact here, and after the interaction a pair of kink lines appear and the surface takes this form. Finally again after a long time at t equal to 60 we find that a pair of kink lines have moved away and again come about to interact. Another interesting thing which we find is that about the amplitude of the surface. The amplitude of the surface here is about 0.4, but it becomes very small at t equal to 60, and this shows corrugational stability of the surface due to interaction of the kink lines. A shock front omega t starting initially as a periodic shape at with m0 equal to 1.2, the front develops complex pattern of kinks and ultimately becomes planar. What I have shown is few applications of the KCl based evolution of a surface, which is nonlinear wave front and shock fronts. There are some references which I list here, and these are available in journals and books. These are 11 references, and I thank you for attention.